Hello everyone, this is class 12th. Topic is how to increase reactivity of haloarenes toward nucleophilic substitution reaction. In previous videos, we have understood our haloarenes are very less reactive toward nucleophilic substitution reaction. Reasons were 5: resonance, polarity, hybridization, electronic repulsion, and instability of phenyl carbocation. How to overcome this problem? The answer is with the help of electron attracting groups. Yes, electron attracting groups can increase haloarenes reactivity toward nucleophilic substitution reaction. Firstly, we should understand what are electron attracting groups. For example, I have a chlorobenzene with me, and suppose nitro group is present here. So if I will draw its resonance, the resonance will be like this. Pi electrons will shift toward this carbon. These electrons are coming for resonance, and obviously these electrons will be pushed and they will go toward this carbon. The next structure will be this. Chlorine will make two bonds now, carrying a +1 charge, and these electrons will come on this carbon as a negative. These oxygens, this oxygen is carrying 2 lone pair and this oxygen is carrying 3 lone pair. Nitrogen is carrying +1 charge because 4 bond it is making. Now, these electrons will be absorbed by nitro group like this. They will make bond here, and obviously nitrogen can maximum make 4 bond. The fourth bond, pi bond, will break and pi electrons will shift toward oxygen because oxygen is more electronegative than nitrogen, like this. The next condition will be double bond here, and now this oxygen is breaking pi bond and shifting electrons toward it. Oxygen will become negatively charged with 3 pair of electrons. This oxygen is already as it is, like this. So you can check this nitro group is attracting electron from a benzene ring during resonance. That's why we are calling it electron attracting group. There are many such groups we have, like cyanide. It can also work as electron attracting group. COH, it can also work as electron attracting group. COH, aldehyde functional group, it can work as electron attracting group. Now what it will do with these electrons? It will return them for the resonance, because resonance means movement of pi electrons. So these pi electrons, next oxygen, this oxygen will give lone pair here, due to which these pi electrons will be pushed toward benzene ring like this, and these pi electrons will be further pushed. So again there will be the movement of pi electrons over entire benzene ring. But watch this point, this diagram. It is attracting electrons from benzene which were coming for resonance. That's why NO2 group is electron attracting group. Now, how we can judge a group is electron attracting or not? Look at this condition. If we talk about groups attached with benzene ring, how we will judge they are electron attracting or not? We should check this atom. The atom which is directly connected with benzene ring should be connected with another atom, and this atom should be more electronegative than A. And between A and B, pi electrons must be there. For example, I have used nitro group, this one. So nitrogen was connected with directly with benzene ring, but nitrogen was further connected with oxygen, and oxygen is more electronegative than nitrogen, and these are connected through pi electrons, sigma and pi electrons also. So such conditions are making them electron attracting groups. So all those groups in which we are getting such condition like this, carbon is directly connected with benzene ring, and carbon is further connected with nitrogen which is more electronegative than it, and through pi electrons. Pi electrons are available. So always check such conditions. If these conditions are available, the group will be electron attracting group. Now Will they work from every position of benzene ring? No. First of all, you need to understand the positions. Like if I am talking about chlorobenzene, the halogen which is attached to a benzene ring, this carbon, the next carbons, these two carbons are known as ortho. They are ortho. Next to ortho, we have meta. And next to meta, we have para. If I change the position of X, means halogen, now these two will become ortho. The carbon which is directly connected with X, you have to check next carbons. They are ortho. Next to ortho will be meta. And next to meta will be para. So three positions are generated according to X, ortho, meta and para. Now from which position our electron attracting group will work? They will work from ortho and para positions. Yes, they can increase the reactivity of haloarene toward nucleophilic substitution reaction only from ortho and para position. Their magic will not work from meta position. This we can prove with some experimental data. For example, this is normal chlorobenzene without any electron attracting group. If we want to convert it into phenol, means if we want to substitute chlorine by OH, means nucleophilic substitution reaction, so look at the condition 6 to 8% NaOH. Obviously NaOH will provide OH negative nucleophile which will substitute this chloride. Temperature is 623 Kelvin and we need high amount of atmospheric pressure also. So the conditions are very much drastic. 6 to 23 Kelvin, very high temperature, and 300 atm pressure, very high pressure we require, because this haloarene is very less reactive toward nucleophilic substitution reaction. So if we want to perform nucleophilic substitution reaction on it, we require very high conditions. But check this. If NO2 group is present on para position and we want to substitute it with OH group. Now check the conditions. 15% NaOH and the temperature is 443 Kelvin now. Only 443 Kelvin you require. Check here how much temperature we require, 623, because it was very less reactive. That's why we need a high temperature to make it active. But here you can check less temperature we required as compared to previous. Why? Because now we have NO2 group with us on what position? Para, which is making haloarene more reactive toward nucleophilic substitution reaction. If you will increase number of electron attracting groups like this one on ortho as well as on para, if they are, check condition, only a normal aqua NaOH we require, means a dilute NaOH solution, and only 368 Kelvin temperature is required, which will convert chlorine to OH. This chlorine is replaced by OH now. Check condition, a dilute NaOH is required and only temperature is 368 Kelvin. Means the conditions are getting milder if we are increasing number of electron attracting groups. And one more, if on all positions, both orthos and one para, then with a simple H2O, means simple water molecule which will give H positive and OH negative, can substitute chlorine even at 323 Kelvin temperature. So substituted product you can make at the place of chlorine, OH will come and nitro will remain on their own positions. So this is the magic of electron attracting groups from ortho and para positions. Will it work from meta? No. Let's find out the reason for that. Reason is, first reason, stability of carbanion. Electron attracting groups from ortho and para positions are making stable carbanion, or they are stabilizing carbanion which is formed during nucleophilic substitution reaction. What does it mean? Check. Chlorobenzene, suppose OH negative is going to substitute chlorine. So mechanism I have already told to you, addition elimination mechanism is happening over here. Suppose OH negative is where we have positive charge, here we have positive charge. This carbon is positively charged, obviously nucleophile will attack on it. Let's attack. When it will attack on it, obviously OH negative is coming with how many lone pairs? 3 lone pairs. For bond formation, 2 electrons are required, which this oxygen can easily donate to carbon. So carbon don't need electrons. Oxygen is bringing electrons for bond formation. So what will happen? These pi electrons will be further shift toward this carbon. For bond formation, 2 electrons are required, which oxygen is bringing. So these electrons will push these pi electrons to this carbon. Not sigma electron, only pi electrons, because pi bonds are easily breakable. They are weak as compared to sigma. So the next condition will be this one. Check carefully. Cl will be there as it is. OH will be there. Negative charge will finish because, sorry, here negative will not come. Its negative charge will finish because it is using one extra electron for the bond formation with carbon. It will donate that electron to carbon. So negative charge will finish from it. What about this carbon? This carbon will become carbonion. NO2 is there. This is the carbonion now. This carbon will become carboanion. Now in 11th class, we have done the concept stability of intermediates like stability of carbocation, carbonion. It is inversely proportional to their charge. If negative charge is increasing, so stability of carbonion will decrease. If negative charge is decreasing, stability of carbonion will increase. Nitro group is helping to decrease this negative charge from ortho position. Check how. If we know the resonance, we can easily understand this concept. We know what will happen. This negative charge means this lone pair will be attracted by nitro through resonance like this. So look how it is helping the intermediate. Check, this will happen. These lone pairs were there which were creating negative charge on this carbon. That nitro group attracted them, due to which the negative charge of carbon, you can watch, it is finished. And that negative charge is transferred to oxygen, because oxygen on the behalf of these electrons, oxygen is pulling these electrons toward itself like this, pi electrons. So negative charge is coming on this oxygen. But what happened? At least the negative charge of this carbon is finished. And right now I said carbonion stability is inversely proportional to charge. अब देखो आप चार्ज कम हो रहा है ड्यू टू नाइट्रो ग्रुप. And this magic of nitro group or electron attracting group is possible only from ortho and para positions. It is not possible from meta position. Let's try. Suppose NO2 group is present on para. Let's check. Can it show this? Suppose I group is on or para position. So let's try again. OH negative is attacking, pi electrons will shift. Very, very interesting concept if you know how to draw resonance. Movement of pi electrons. Now, this is a negative charge. Carbonion is generated. Will nitro group help it to decrease the negative charge? Yes. Watch. Obviously, these electrons will go for the resonance. And these pi electrons will shift on this carbon. Pi bond will come here, double bond. And here we will have negative charge. NO2 is our neighbor. Now NO2 will help. How? These extra electron which are creating negative charge on this carbon will be attracted by it in this fashion. उसी तरह से जैसे ऑर्थो पे इसने इलेक्ट्रॉन अट्रैक्ट किया था, अभी भी वैसे ही इलेक्ट्रॉन अट्रैक्ट करेगा ये. डबल बॉन्ड विल कम हियर. एंड यहां ड्रॉ कर देता हूं नेगेटिव ओ नेगेटिव. तो द नेगेटिव चार्ज ऑफ दिस कार्बन, पहले जो नेगेटिव चार्ज आपको दिख रहा था, हियर वी हैव अ नेगेटिव चार्ज, इट इज अब्जॉर्ब्ड बाय नाइट्रो ग्रुप, ड्यू टू विच the stability of carbon ion is increased. The negative charge is decreased through nitro group. That's why stability is increasing. So nitro group is helping this attack, because after this attack carbon ion was generated. That carbon ion was creating problem. What problem? Instability. But that instability was decreased by nitro group. So nitro group is enhancing the reaction by its electron attracting nature, and this it can do only from ortho and para positions, not from meta. Let's check why not from meta. Suppose our group is on meta position. This is meta position. OH negative is attacking on carbon, due to which pi electrons are pushed. Next structure is this one. Carbon ion is ready. NO2 was waiting, but will it get electrons? Let's check. These electrons will go for bond formation, and these pi electrons will move forward like this. And lone pair will come here. Negative charge will generate here. Here will be a pi bond. Rest as it is. Nitro group बस देखता रह जाएगा. चेक. हाथ कुछ नहीं आने वाला उसके. ये इलेक्ट्रॉन यहाँ आए, और जो आगे के इलेक्ट्रॉन्स थे पाई इलेक्ट्रॉन, वो आगे शिफ्ट होंगे, नाइट्रोजन की तरफ शिफ्ट नहीं होंगे. Due to repulsion, here we have electrons. Obviously the pi electrons will shift to next carbon, not toward nitrogen. Means from meta position, nitro group is unable to attract electrons toward them. Not only nitro, every electron attracting group is unable to attract electrons from meta position. So that's why we are saying nitro group can increase the reactivity of haloarenes when it is present on ortho and para position, because from those position it can make carbon ion stable, which was generated due to attack of OH negative. From meta position you can watch, electrons will not come. You will say, sir, try from this side. Some students obviously will have some curiosity that if we, because benzene ring is this is also a benzene ring. So try like this, anti-clockwise you were moving clockwise. So due to clockwise rotation, electrons are not coming on this position. Let's try with the anti-clockwise position also. Check by yourself. They will not come on meta position. Let me draw it. चेक कर ही लेते हैं आते हैं कि नहीं. This will be the next movement. Due to next movement, unpair here. Let's attack OH negative first. Na? Why we are moving chlorine electrons? OH negative will attack, then they will move. Nitro group is waiting, NO2 is waiting. Okay, atom to bond, bond to atom. दूध का दूध और पानी का पानी. Negative. NO2 is waiting. Now what will happen? These electrons, atom to bond, and these pi electrons will be pushed further. Now are we getting electrons on this carbon? Nitro group will keep on watching these electrons while they were passing from it, because नाइट्रो ग्रुप इज प्रेजेंट, बैठा ही उस जगह पे जहाँ पर इलेक्ट्रॉन्स आने ही नहीं वाले, मेटा पोजीशन. अगर ऑर्थो और पैरा पे होता तो वहाँ इलेक्ट्रॉन्स आते और वहाँ से इलेक्ट्रॉन खींच लेता और कार्बोनाइन को क्या कर देता, स्टेबल. मीन्स this carbon ion cannot be stabilized by nitro group. And if carbon ion is not getting stability, the OH negative will not prefer to attack on this chlorine because it know that after this attack the molecule will become unstable and nitro group is not helping. So whenever nitro group is present on meta position, haloarenes reactivity toward nucleophilic substitution reaction will not increase. Now next reason we will check in next video.